And so we see these chondrocytes here scattered throughout. The little spaces they live in are the lacunae. This pink stuff in between represents an extracellular matrix that they produce. As you get to the periphery of a cartilage mass, that cartilage matrix is surrounded by a pterochondrium of connective tissue. And you can also often see resting immature cells, or chondroblasts, adjacent to that pterochondrium. These chondrocytes are often found in little clusters called isogenous groups. That's just, remember, because of the way they grow, as they continue to divide, they form these little clusters, so they're often bilaterally symmetrical. So those are just the little isogenous groups of the chondrocytes within their lacunae. And remember, this is the first type of cartilage, hyaline cartilage, which has a very glass-like appearance. So when you look at hyaline cartilage, the background matrix looks kind of like pink frosted glass, and it's reinforced with abundant type 2 collagen fibers. Hyaline cartilage looks different from fibrocartilage, which, while it also has type 2 collagen, also has a lot of type 1 collagen. Basically, fibrocartilage is hyaline cartilage with lots of connective tissue added. So it has this very grainy, granular appearance to it, and it's also much less cellular. So you'll see many fewer chondrocytes within fibrocartilage. When you get to elastic cartilage, now the background might look like hyaline cartilage, that kind of pale frosted pink, but it has the addition of elastic fibers that have been added to it. And so you see all these very bright pink fibers overlaying that type 2 collagen. And these elastic fibers, remember, on a special stain, would look black. It would look like a black cobweb or a lace, kind of a meshwork there. Still the same chondrocytes within their lacunae. Elastic cartilage has kind of a limited distribution. We see it in places like the epiglottis and larynx, the eustachian tubes, places like that. External ear canal. Bone is essentially cartilage, hyaline cartilage, which has undergone further mineralization. So it has lots of mineral salt, hydroxyapatite deposited within it. Bone has a couple different varieties. So we have, for instance, woven and lamellar bone. Woven bone is the first bone which is produced, has very disorganized collagen. After it is remodeled, the bone takes on a more uniform appearance, or a lamellar appearance, where you can see these concentric layers. Question?
Do you call woven and spongy the same thing, or?
You kind of can, sort of. Spongy bone actually undergoes remodeling also over time, but granted, it looks much more like woven bone. So if you call it spongy bone, woven bone, I'd probably let you slide. Just like cartilage, bone is also surrounded by a connective tissue layer. In this case, however, it's called a periosteum instead of a perichondrium. So connective tissue on the surface of the bone. This periosteum is sometimes is anchored to the bone by fibers called Sharpie's fibers, which really don't show up well, so don't worry about identifying. When it comes to types of cells within bone, we have primitive osteoprogenitor cells, which can be a little difficult to distinguish individually. Basically, they're just big, darkly staining cells. What you should be able to recognize are the osteoblasts. These are the osteoprogenitor cells which have undergone some differentiation. They're beginning to produce extracellular matrix. And these osteoblasts are often found around forming spicules of bone. Here we have some very nice views of these osteoblasts. Remember, large, darkly staining cells. And they initially produce an extracellular matrix which is unmineralized and very much like cartilage. That unmineralized matrix is called osteoid. And as it mineralizes, it undergoes a slight color change to become mineralized bone. And that process occurs as a result of alkaline phosphatase, which causes these minerals to precipitate out into the matrix. Here we have a special stain which highlights very nicely these osteoblasts. They often row up, almost like a row of bricks at the edge of a wall. Here you can see the unmineralized matrix in pink, and then the mineralized bone in this nice turquoise color. During this process, some of these osteoblasts invariably become trapped within the matrix that they're secreting. Once that happens, they will then mature into osteocytes. So these cells, which become trapped within matrix, within lacunae, within the matrix, are the osteocytes. And that's just more osteocytes. Now, in addition to osteoblasts, which secrete bone, we also have osteoclasts, which break down bone. Their job is to chew up bone so it can be remodeled. And so the osteoclasts are very large multinucleate cells, part of the monocyte macrophage lineage. And here we see one in H&E, and here we see another one on a special stain. Because these cells are literally chewing away at the bone, they are very commonly located in depressions on the surface of the bony spicules, and these depressions are variously referred to as Cauchep's lacunae or resorption bays. And so, while this one is actually chewing on a little process here, you can see this osteoclast is in fact in a little depression. And note, here we have osteoclasts and osteoblasts side by side. So this little spicular bone is having a bone formed on this side of the process and removed on this side. So essentially it's being remodeled to change its overall shape. And that's the whole point of bone remodeling in general. Here we have just some more views of osteoclasts. Here's a couple of nice pictures of osteoclasts. EM view. The point of bony remodeling is to form what are called conversion systems or osteons. These enhance the strength of bone. And so when you look at a conversion system in cross-section, you see a central canal, or conversion canal, which would contain blood vessels and nerves in real life. Most of these are thin sections, and so as a result of that processing, the soft tissue is lost. And so you often can't see the blood vessels or nerves in the middle, and that's why they look empty. This represents bone. Okay, you can see these dark spots represent osteocytes, the mature bone cells, which are present within their little spaces, their lacunae. These individual osteocytes have extensive cytoplasmic processes, which are which live within these little tiny spaces within the bone called canaliculi. And so when you look closely, you can see this would look almost like little radiating lines or cracks. Those are the canaliculi that contain these cytoplasmic processes, which allow these osteocytes to communicate with each other. At the outer edge of the conversion canal, you can see kind of a rim, which is called the cement line. That represents the original tunnel that was dug by the osteoclast. Okay, and then the osteoblasts move in and start secreting bone and mature into osteocytes, yada yada. This is another view showing you diagrammatically these osteons or conversion systems. You can see the central conversion canals, and you can also see the cross-linking Volkmann's canals. This is a very low-powered view through the shaft of a long bone, showing you the spongy bone within the medulla and this lamellar bone of the cortex, and you can see some of these conversion systems. They're quite numerous within the cancellous bone, or within the compact bone of the cortex. Once again, a medium view and then a higher power view showing you the individual osteon, the cement line, conversion canal, etc., etc. At the level of the metaphysis within long bones, we have a growing zone called the epiphyseal plate. This plate remains unmineralized in early years until the final size of the bone is reached in adulthood, and then this plate closes or becomes fully mineralized. In open epiphyseal plate or unmineralized plate, you can see several zones or regions within it. This is the articular end, this is the diaphyseal end. At the articular end, we have a resting zone or a zone of reserve cartilage. It's basically just chondrocytes hanging out, and then next to it we have a proliferating zone. This is where we have chondrocytes undergoing successive mitotic divisions, so the cells start to line up and form these rows. After they divide, they then mature, so we have a zone of maturation, and then the cells, after they mature, they begin to produce product. They begin to produce lots of glycogen. And so as they produce more and more glycogen, the cells enlarge, they become very highly vacuolated, and they hypertrophy in the zone of hypertrophy. Eventually, they die. And as the cells die and degenerate, now these empty spaces become infiltrated by osteogenic cells that migrate up to the marrow. So we have the zone of degeneration, and then as these osteoblasts start producing extracellular product, matrix, we develop this ossification zone, and then finally the production of these bony trabeculae, which result in mature bone and eventual closure of the epiphysis. To allow movement within the skeletal system, we have joints. Movable joints are synovial joints. So here we have a typical synovial joint, articular cartilage covering the ends of the bones. And then surrounding that, we have a joint capsule lined by a membrane called a synovial membrane, whose job it is to secrete synovial fluid, which acts as a lubricant for the joint. Here we have another type of joint, a non-movable joint, a fibrocartilaginous joint, specifically an intervertebral joint. Intervertebral joints are characterized by a softer central region called the nucleus pulposus, surrounded by a more densely fibrous annulus fibrosus. Okay, lymphoid organs. Lymphoid organs, remember, have lymphatic vessels which supply them. We've already talked about those. The first lymphatic organ you should be able to identify as a lymph node. Lymph nodes characterized by an outer cortex, inner medulla. That cortex contains primarily B cells. Remember, most lymphoid tissue is aggregates of B cells. That little extension of cortical tissue, these little darker areas within the medulla, are referred to as medullary cords, whereas these white spaces between the medullary cords and the medullary sinuses allow blood and lymph to percolate through the lymph node. Lymphatic drainage within the node is accomplished by various sinuses. So we have an outer subcapsular sinus. Here's our cortex. Notice within the cortex we have these various follicles. So these little foci, dense aggregates of B cells, are primary follicles. If they contain a paler central region, a germinal center, they would then be called a secondary follicle. So here we have a nice view of a secondary follicle with its germinal center within the cortex. If you look at a high power view of the medulla, you can see these medullary cords separated by these paler staining medullary sinuses. In this case, they're full of lymph. Here's an example of one of those lymphatic nodules. In this case, it has a germinal center, so it's a secondary follicle. If it has a germinal center, that means that node is undergoing clonal expansion. Those lymphocytes, the B cells, have been exposed to antigen. They are gearing up to produce lymphoblasts, which are going to mature into B cells that produce antibody or plasma cells. And then that region will be surrounded by a thin, darker staining mantle zone, which is a region of antigen presentation. The thymus, at first glance, looks a lot like a lymph node, except for two key characters. One, it has much more dramatic connective tissue septi separating these lobes of the thymus. And also, it has Hassel's corpuscles. These Hassel's corpuscles are visible even at low power. These are eosinophilic lamellated structures which represent degenerate reticuloepithelial cells. Here you can see them at high power, typical Hassel's corpuscle. And a very important thing about the thymus is that the thymus, unlike most other lymphoid organs, contains aggregates of T cells rather than B cells. As you mature, the thymus becomes infiltrated by fat and undergoes fatty infiltration or thymic involution, follicular degeneration. And so here we have an adult thymus which has undergone involution and been replaced by fat. It's just these little remnant islands of active tissue. Next up, we have the spleen. The spleen is separated into red pulp versus white pulp instead of medulla and cortex, like we saw before. So we have the red pulp being areas of red cells, and the white pulp being foci of white cells. The spleen is also surrounded by a very thick, dense connective tissue capsule, which extends throughout the body of the spleen as these very thick connective tissue trabeculae. Some of these trabeculae may contain blood vessels, so you can have trabecular arteries or veins within these vessels. Here we have, once again, these areas of white pulp within the red pulp. White pulp very commonly contains a central artery which supplies that area of white pulp. Most of these are going to be B cell foci.